Hey, knowledge lovers! Today we're reviewing the Reinforcement Learning Specialization, a rigorous, hands-on path that takes you from MDP basics to building a complete RL agent. The link to access this course is in the video description. Let's dive in. What this specialization is about. Created by the University of Alberta, this 4-course sequence teaches you how learning from interaction actually works. You'll formalize sequential decision-making problems as Markov decision processes, work with value functions and Bellman equations, and implement core algorithms that let an agent learn by trial and error. The emphasis is on small, interpretable problems so you truly understand the foundations before scaling up. Along the way, you'll see where RL sits in the ML landscape, how it complements supervised and unsupervised learning, where it pairs with deep networks, and where simpler function approximation is the better teaching tool. You finish with the skills to design an RL approach for a real task and to evaluate it responsibly. Module 1, Fundamentals of Reinforcement Learning. You'll define MDPs, policies, returns, and discounting. Then compare Monte Carlo and temporal difference prediction. Control methods like SARSA and Q-learning introduce the exploration-exploitation trade-off, and on-policy versus off-policy learning. Assignments focus on implementing these algorithms from scratch, visualizing convergence and diagnosing instability, habits you'll rely on in later courses. Module 2, Sample-Based Learning Methods. Here you dive deeper into data-efficient learning. You'll implement n-step returns, eligibility traces, and planning with Dyna, blending real experience with simulated updates from a learned model. You'll also examine how sampling affects bias variance and learn when to prefer on-policy updates, off-policy updates, or model-based planning. Critical judgment calls in applied RL. Remember, if you're interested in the course, you'll find the link with the best price in the description. Module 3, Prediction and Control with Function Approximation. Scaling beyond tabular settings. You'll approximate value functions with linear methods, e.g., tile coding, Fourier bases, and manage stability with step sizes and regularization. You'll see why naively mixing bootstrapping, off-policy data, and function approximation can diverge, and how to mitigate it. The focus is building agents that generalize across large or continuous state spaces while remaining inspectable, a perfect stepping stone toward deep RL. Module 4, a complete RL system. You'll put the pieces together, define an environment and reward signal, choose a representation, train and tune an agent, and evaluate with learning curves and baselines. The capstone stresses experimental rigor, fixed seeds, proper averages, and fair comparisons, so your conclusions hold up. You'll submit a concise report that explains design choices, ablations, and failure cases. Who this is for? Ideal for data scientists, ML engineers, and researchers who want a principled RL foundation. You should be comfortable with Python, basic probability, and linear algebra. Calculus and some prior ML help, but the courses are designed to build intuition first and math detail second. My honest take: big strengths, world-class instructors, a clean progression from tabular to function approximation, and from-scratch implementations that force real understanding. You'll also learn experimental discipline, a rare but vital skill. Watchouts: the focus is foundational RL, not a survey of the latest deep RL tricks. If you're here only for giant Atari benchmarks, you'll find this slower, but you'll leave with skills that make advanced papers and libraries far less magic. You can obtain this specialization without a one-time payment, simply by purchasing a Coursera Plus subscription, which offers access to this course and more than 7,000 other courses by paying a monthly or annual fee. The link with the best price will be in the video description. Until next time, knowledge lovers.